throw out people who get an absolute zero. All right, those don't really count because that's a no effort thing. And then those that actually did take the tests and scored, all those statistics will be calculated. All right, I can't just use a bunch of zeros. If people don't take it and get a zero, or turn it with their name on, that really can't be used for a meaningful statistic. But I'll get back to you on this. Now, today, well, I'm going to, first, were there any questions about the homework? I gave you things on Thevenin, right? And Norton. Were there any questions at all? I hope you're keeping up with this. Anything at all? Remember, this is complex numbers with Thevenin and Norton. I gave you 5 problems, I believe. Remember? Y'all do? They're straightforward if you did them, but if you didn't and you wait to try to learn this stuff, it's going to be kind of difficult. And that's the thing I'm going to keep on emphasizing, the importance of doing the homework when it's assigned before the next class period. Otherwise, it's going to hurt. And it gets worse quick because now we're going to get into power. Yes, sir.
4.56.
4 point what?
56.
Yeah, sure. I really wanted to do one of them at least. It says solve problem 441 using Thevenin. So 441. This is problem. We're going to have voltage here, plus to minus, and that's 6 at 0 degrees volts. And then they have a resistor of 1 ohm. And then they have a capacitor here of minus J1 ohm. And then they have a resistor of 1 ohm. And then they have a current source here of 2 amps, I believe. And they want the voltage across the resistor, the 1 ohm resistor that's right here. This is what they're after, this voltage. So I'm going to use Thevenin's method of analyzing this circuit. All right? Now make sure you know Thevenin's and Norton's. I haven't asked you anything about that on the test, but it's coming up. The next test you'll get that stuff. And probably in future quizzes. So the first thing I have to do is identify the load. Does everybody see that R, in this case it's R load is just 1 ohm. Everybody got that? Now what Thevenin's theorem says is after you identify the load, you remove it, and I'm going to. And now we look for the open circuit voltage here, or V Thevenin. So this is step 1, step 2, V open circuit, which is V Thevenin, right? And now I need this voltage, plus to minus, right there. You all see what I'm talking about, class? Can you see the far back? If you cannot, for whatever reason, yell at me. I'll write as big as I need to. All right, now how am I going to get that? Here, you go through the logical steps. You have a current source. That means that current is flowing no matter what. You follow me? That's given. If we have that current, can any of that current flow this way, class? Why not?
Open circuit.
It is an open circuit here. Current needs a closed circuit. It needs a resistance there. Follow me? So no current can go this way. You all see that, class? Current must go this way. Follow me? If it goes that way, what's the voltage here going to be? You all agree 2 amps is going that way, right? The resistance there is 1 ohm. What is the voltage? It's going to be what? 2 times 1 or 2 volts. Does everybody see this? I'm not trying to do something here that's going to embarrass somebody. These are just obvious things you have to see. Everybody with me? Now, once I have that, the next thing is how much current's flowing here? Again, 0. 0 times minus J1 is still 0, is it not? In other words, there's no voltage drop across that capacitor. Does everybody see that? So we're ready to figure out the open circuit voltage. We start here. Now, can I go this way, class? Why not? It's a current source. You don't sum voltages through a current source. You don't know what it is. Everybody here knows. That's a common mistake. You go this way. And when I go this way, what do I see? An increase of
6.
And then an increase of
2.
And then nothing, right? Or we get 8 volts, open circuit voltage. How many see this? Make sure you can go through these steps methodically and easily. So that's going to be simply gonna be 6 plus 2 or 8 volts. Now that's real important. The third thing with Thevenin is to find R Thevenin, right? Let's make sure we get this. I'm glad you asked that question. I think we should do another one just because I'm not seeing the certainty. Usually by this time, the kids, everybody just says, oh, we got it. They just pound this stuff. But I'm not hearing that. Yes, miss?
Why in particular is it plus 2 volts, not minus the 2 volts?
It's plus 2. It's gonna start here and go plus 6, plus 2.
Like, how did you determine the direction of that?
Current is flowing this way, right?
Okay.
Positive current flows into the positive terminal of the resistor. Make sure you have that. Everybody with me? Did you have a question? Did you have a question, guys? If you do, ask it. Don't be. I'm level with you. If you've got things with your calculators still, if you have problems with your calculators, then make people aware of it, and we'll put you together with somebody who knows what they're doing. Yes, sir.
So do we treat this any differently than mesh analysis?
Well, remember, we're doing Thevenin. It's completely different because with Thevenin, you first identify the load, then after you identify the load, right? You're not summing voltages around a closed loop and setting them equal to 0. What you're doing is finding the voltage across the open circuit. So there's no summing around a closed loop and setting it equal to 0. That's mesh.
But do you treat the resistors differently for the different methods? 'Cause
Well,
it seems like for mesh,
you're asking a question that is a clumsy thing. You're trying to say, is there something different about mesh analysis compared to this? Yes, there is, and here's why. In mesh analysis, you would take the sum of the voltage drops around a closed loop equal to 0. In fact, I'm doing that, but I'm not doing that. I'm not stating that because this voltage drop I break out entirely by itself. All right? So if I do this, it's just, I always say, and this is the easiest way, guys. I've been doing this for a long time, taught it many times. Start at the negative terminal, find all the voltage drops or increases until you get to the other terminal. That is the voltage between the negative and positive terminals. You all hear me on that one? It's the way to do it. You could set the whole thing equal to 0, and yes, that is in fact what I'm doing, but it's easier, I think, to see.
it was more for me, I always seem to slip up the signs on the resistors.
Well, here's what you can do if you went all the way around. You would say an increase of 6, an increase of 2, 0 volts, and then a decrease of VOC all equals 0. VOC would go to the other side, it becomes positive. With me? That's all I'm doing. Okay, now, what is this going to be R Thevenin? First, what do we do with the sources when we want Thevenin equivalent resistance, class? Turn them off. A current source becomes a open circuit. Just think if you turn off current, there's no current flowing through, it's an open circuit. When you turn off a voltage source, it goes to 0 volts. It's a straight wire. Follow me? Right? Now, what's the resistance between this terminal and this terminal? It's not complicated. Does this have any part of it? No. What do you see? You got 1 ohm and minus J1. Do y'all see that? So R Thevenin here, or Z Thevenin, not R Thevenin, but Z Thevenin, it's an impedance, is simply going to be 1 minus J1 ohms. Follow me? It's not hard, but until you do some of these, you are going to be stoned, you're going to be just stumped. It's the first time you did it. Sorry about that. I was going to be stone cold, stop, but when I hit this, what do I do next?
You plug back in.
Now you've got to build a circuit, right? You start by putting the open circuit voltage here, plus or minus VOC, which we have. Then you put in the net impedance Z Thevenin right here, right? And I'll put it in a second. Then you come down here, and now you reinsert the load, which was 1 ohm, right? And they wanted this voltage, so this is actually what I'm after, that voltage. Do you all agree? Now, I didn't even put in the values yet, but I'm going to show you something, and this should be obvious. Do you all see here, once you have open circuit voltage, the only thing left to do is voltage division? The only thing I need to do is divide the voltage to get this, don't I, class? I can say that V out is really VOC, and then it's going to be times this, in this case 1 ohm, or whatever the load is, over Z Thevenin, right, plus 1. That means that my V out will be equal to V open circuit, which is 8 volts, right? Then it's going to be times 1 over Z Thevenin, 1 minus J1 plus 1. You can see that's going to be 8 times, really, 1 over 2 minus J. And you can give that to me in polar. I might as well get used to using your calculators. Give it to me in terms of a polar number there. So I've got 8. This is supposed to be an 8. 8 times 1 over 2 minus J. It's really 8 divided by, what is that going to be? The square root of 5. And it's going to be at an angle, it's like 53.7 degrees or so, minus 53.7. But just magnitude and angle, if you don't mind. Make sure you know how to use your calculators to do this efficiently. If you got them, use them. It's the only way to really get this down. Anybody? Anybody? It's really not that tough, I don't think, is it? I just want to, yeah, what do you got?
3.57 at an angle of 26.57.
What angle?
3.57 at an angle of 26.6 degrees.
26.6 degrees? Anybody confirm that?
That's right.
All right, good. So that's how we do that problem, using Thevenin's method, right? I want to do another one because I don't think, yeah.
So we haven't really done much with Norton's. How would you?
We'll do Norton's, how's that? I'm glad you asked. Norton's is almost like, I don't usually go for Norton. Norton's looks for the short circuit current first, not the open circuit voltage. So what Norton does is, his theorem says this. This was 1 ohm, and this is where we wanted the actual VOC, right? And this is a current source. That was 2 amps at 0 degrees. Is that correct? Oh, this is 6 volts, wasn't it, class?
Yes.
Plus or minus 6 volts at 0 degrees. So that's the original thing. And question about Norton. I'm going to say this, most of the time I ask Thevenin, sometimes it helps to do something with Norton, but you're going to see source transforms allow us to do, Norton is a source transform of Thevenin's circuit, if you want the truth. All right, but I'm going to do the Norton. Norton's theorem says instead of the open circuit voltage, first you identify the load. So the first thing is still identifying the load, and our load is 1 ohm, so that's that. Then you remove it, as before. But now, you don't look for the open circuit voltage, you look for the short circuit current through there. So with Norton's method, you had some problems like this, you short that out. And now you want I short circuit here. So now I'm looking for I short circuit, not the open circuit. Well, how do I get I short circuit there? This is a little trickier, isn't it? How do I get it? Remember, this is what I want right there. I'm going to just show you guys a quick one. I mean, I've done these too many times. Now, somebody, I think the guy that said use a source transform or something like that. But here's the thing. Do a source transform right here. You see how you got 6 and 2 ohm and 1 ohm, right? Just make that, watch this. This becomes simply, now it's 6 volts by 1 ohm, or 6 amps, right? At 0 degrees. Now I put the 1 ohm here, correct, class? And I tie that together. Y'all follow me? I'm going to see what I've done, make sure you understand. Y'all with me on that? I did a simple source transform, didn't I? In the back, you guys see this. All right, now that source transform does something really easy. It helps me because I can take the 6 and the 2 together and get a total of 8 amps flowing there. How many see that? Are you with me that you've got 6 here and 2 here all flowing to that upper rail? That's 8, so just erase this.
Wouldn't it?
And make this 8 amps. And now what? You have 8 amps and it divides between these 2 impedances, doesn't it? They're in parallel. Yes, sir.
Would it not be 4 amps because they go against each other?
They're both flowing into this thing, right? They're flowing in and flowing down here.
Oh, so they're going in separate loops.
I mean, that current's absolute. It's not, that current's going up. It's not a mesh current. That is the current that's flowing into the upper rail. Everybody see this right here. Important you do. Now, you all agree I have 8 amps there, first of all. Now, and these are in parallel, right? So now I'm going to use current division, right? That's a basic thing we studied in the first 2 weeks. So current division says to get that short circuit current, I take the total current, 8 amps, right? And I multiply it by the opposite impedance, 1 ohm, divided by the sum of the two, right? Divided by 1 minus J1. That's gonna give me a current, right? That's gonna be what, 8? And it's gonna be divided by the square root of 2 in magnitude. That angle's minus 45 degrees. Upstairs, it's gonna be at an angle of plus 45 degrees right here. With me? That's just the magnitude and angle of the short circuit current. Everybody got that? Now, after that, now I did a source transform here. I'm gonna put the thing back where it was. After that, I'll do this. I'll say that was 1 ohm, right? And that was a total of 6 volts, and that was 2 amps, right? Everybody with me on that? That's the original. Now when you look at this, I still need to get R Thevenin. You notice that R Thevenin is going to be the same whether it's a Norton or Thevenin problem, right? Always the same. We know what R Thevenin is. That goes away. I'm looking for this now, the Thevenin equivalent resistance between these 2 points. That becomes a short circuit, and it's simply 1 minus J1 as before. So the third thing is our Z Thevenin. I call it R Thevenin. Z Thevenin is just 1 minus J1 ohms. Everybody see that, class? It's the same as before. Now what do I do with Nortons? If you don't know, this is good. I'm hopefully answering a question. Now I set up a Norton equivalent circuit. I go ahead and I put my short circuit current here. Then I put my Z Thevenin right here. And then I put my load, which was R here, which was just 1 ohm. That's going to be my RL. And this is the place where now I could put in any load there, and this part of the circuit is effectively replaced by 2, and only 2 things. It's going to source current and an impedance in parallel with it. Follow me? With a Thevenin equivalent circuit, once you took the load off, you replaced it with a Thevenin voltage source in series with a Thevenin impedance. Here, it's going to be a Thevenin current, I should say a Norton current right here, short circuit current, in parallel with it, and we want the voltage here. Now, this RL is 1 ohm, right? If I want that voltage, there are so many ways to get it, but I'm going to say this. Here I know Z Thevenin is 1 minus J1, right? All right, now, if I put in 1 minus J1, y'all see one way we could do it is just get an equivalent impedance and say that equivalent impedance times the short circuit current would be the voltage, and it has to be the same on both. That's one way to do it. Another way you could do it, take the short circuit current, do current division, find out how much current goes in the 1 ohm, and then multiply it by 1 ohm. You all see me? What's going on? There's many ways probably to do this. It essentially is all the same thing. Yes?
If you were writing that circuit down and you saw and used the wrong polarity for that resistor, would it show up as a negative voltage?
Well, resistors don't have polarities. All right. Resistors are just resistors or resistors. When you put a polarity in, it defines what you consider the positive versus the negative point of measurement. So you put them in, the resistors don't have that. I know you think, well, the resistor here, see, the way the short circuit current goes, it's from a positive to the negative terminal. The original problem had this as the polarities for the voltage. So the short circuit current would be going from the plus to the negative terminal through there. Good. That helps. Okay. All right, now, yeah.
If you wanted to find the voltage drop across the 1 ohm resistor on top, was there an easy way to do that from what you've already done, or do you have to do a whole other analysis?
Well, first, this is an interesting point. The whole purpose of Thevenin or Norton is to eliminate the circuit itself and really boil it down to 2 components, a source and an impedance. And then any load you stick in where that load was, you can analyze quickly. So you can't go back and say, well, we can calculate this now. No, that would come from a mesh or nodal analysis, all right? Just remember that. Yeah.
Does it matter which way we kind of walk around the circuit when we do
You can't sum voltages through a current source. Yeah.
I mean, like when you went for Thevenin's, when you went the negative to the plus.
Oh, you're saying This is a good question. He's saying, well, look, you went this way. Will it change this way? No. It's just the same. It's the impedance between the terminals. It'll be the same. It doesn't matter which way you go. Impedances, you just,
I was thinking, cause you'd have.
they don't have a polarity.
Okay.
Impedance is 1 ohm, period, or minus J1 ohm or plus J1 ohm. There's nothing else besides that, okay? All right, now, finally, to get this, let's go ahead and get this. If I want this voltage right here, here's what I do. If I want V out, I'm gonna take that short circuit current, take I short circuit right here. Then I'm just gonna go ahead and say, I'll do current division, so I'm gonna take the opposite, 1 minus J1 over this plus this, or 2 minus J1. And that will be my V out, because that's the current through there times 1 ohm. I don't need a 1 ohm. Follow me? If I get the current flowing through the 1 ohm, multiplying by 1 gives me the voltage. So I don't need to do that. Are you with me? And that will give you the same value as before, whatever it was. But you can do that yourself. Are you with me? And that's the short circuit current right here. You can stick it in and you can see for yourself it does work. Now Norton, if you really want to know the truth, Norton, when you have a current in parallel with impedance, that can be transformed to a voltage in series with a resistance. So if you got one, you got the other automatically. Do you follow me, class? Everybody follow me on this? This is important. And you will be asked about this kind of stuff. All right, but I tend, for the record, to lean towards Thevenin. In general, in my opinion, it's easier usually, all right? Because when you have an open circuit, it's easier to get that voltage than a short circuit for a short circuit current, right? So just for the record, if you want to know how to win it. All right, let's do one more problem before I move on with power. Here's another thing. People are going to be in different ways. They ask this question in a lot of different ways, but it's essentially the same thing. What can I do to help myself? This is one of the things Dave Irwin, who wrote this book, told me years ago, and what I'm referencing right now. He said that go and do a problem. Like if you know how to do a problem with mesh, right, or node, take that same problem and do it with the opposite node. If it was mesh you started with, do it with node. Make sure you get the same answers. Then use Thevenin's theorem. Right? Then, well, you can use Norton, I wouldn't at that point, but then go ahead and do it with superposition. When you confidently can get the same answers using all those methods for a single problem, then you're going to feel very comfortable moving on. It's when there's questions, doubts, inconsistencies, I get it with node, I don't get it with mesh and stuff, then you need to start exploring where your problem is. If you can do them with any of the methods, then, go through all those problems, you won't have a problem with this stuff. But if you stumble with certain methods, you're going to have trouble. Because we're going into an area very shortly where it's going to be essential that you have absolutely no trouble with the prior material. Because the next part gets a little more complicated. So I want to make sure I underscore that fact. And you have plenty of problems. I must have given you 3 or 4 pages of problems with complicated, complex numbers. You can go back and do them all if you want, if you have that kind of time with all the different methods. And that will almost seal the deal for just about anybody, if you want to know how to study. But it takes time, and it doesn't happen quickly. If you don't understand something, you can come see me. Next one I'm going to do, let's see, that was, I think we can do 439. Let me take a look at what it is. Yeah, this is. We did 438, right? No, we didn't. Actually, why don't we do 438 with Thevenin's and then we'll move on. 438 does this. So we got 12 and 6 volt sources. We're gonna do one of this one. They want the currents, but I'm gonna cut this problem up and make it a little different. I'm gonna say I want the voltage across this component. So that's my goal with Thevenin. I can't ask for 2 currents with that. That's my goal. I want that voltage. Let's do it with Thevenin together. First thing is what? You locate the load, right? My load, call it Z load, is equal to minus J1 ohm. That's 1. Number 2, you remove it. So the second thing I do is remove it, huh? And then I want the open circuit voltage there. Now this one is kind of interesting. You can do this so many different ways. And some people are going to say, well, which way do you want me to do it? It doesn't matter, but you know, you could do a couple of source transforms. You all agree? Source transforms, then combine the 2 impedances together into one, and then you could easily get the voltage there. You could, you'd have 2 current sources in parallel with the 1 and the J1. You could do that. You could go ahead and just do some of the voltages around a closed loop, which somebody's over there, you're an advocate of. That's fine, follow me? But you should feel very comfortable if asked to get this voltage, you can get it. The key is how much current is flowing here. Class, how much current is flowing through this 1 ohm, please? It's 0. Make sure you know that, right? It's an open circuit. There's nothing there, current can't flow. Got it? Make sure you see this. If you don't, then come. All right, now, how do you want to do it? Well, how about we do it this way? We'll assume a current I there. So I has to flow all the way around. We'll solve for I, and then we'll get the voltage drops. Is that all right with everyone? All right, I'm going to start right here in the lower, really left-hand corner. So I'm going to get the voltage drops. I get an increase of 12. Everybody agree? Then I get a decrease of what? Minus just 1 I1, right? Call that I1. There's only 1 I. But you agree with that? What else? Then it's going to be minus J1 times I1. That's the voltage drop here, correct? And then what else? It's going to be minus 6, right? This whole thing equals 0. Agreed, everyone? I'm just making sure everybody sees it. It's not hard, but I got to make sure everybody sees the details. You write that equation. Now I'm going to solve for I1. Well, I can see that 12 minus 6 is going to be 6, right? Taken to the other side would be minus 6. And that would equal what? Minus, or really I'll just put I1, right? And that's minus 1, right? Minus J1. And I should get that. Do you all agree with me, class? Now at this point, what I'm likely to do, and I think a lot of you were doing this, but I can't say it's certainty, is get rid of this minus sign. I can make that go away. Just because I don't like it. Then I can find out what I1 is, right? That would be 6 over 1 plus J1. And that's really what? That's going to be 6 over the square root of 2 at 45 downstairs at an angle of minus 45 upstairs degrees. Y'all agree with me there? Right? 1 plus J1 has a magnitude of square root of 2. The angle is 45 degrees. Do you follow me? If you have 45 degrees in the numerator, or in the denominator, when it comes to the numerator, the sign changes. Therefore, it's going to be minus 45. How many see what I've done there with that angle business? Y'all with me? Yes or no, just help me out. How many do see it? All right. It's straightforward mathematics. If you have a plus jb, the magnitude of that number is the square root of a squared plus b squared. The angle is an inverse tan of the imaginary coefficient divided by the real coefficient. That's it. Well, I know if I have 1 J1, the inverse tan of that is 45 degrees, just from experience, not tricks, okay? That's how I got that. Now if I have that, to get the open circuit voltage, how am I going to do it? Y'all agree that that's the right answer for current, all right? All right, now it's a little messy, it's not easy, but if I want the open circuit voltage, V open circuit, watch this. I'm going to start, it doesn't matter which way we go, I'm going to go here. You see it's an increase of 12, right? So I have an increase of 12. Here's where your calculators, you should get out and make sure you can do this. then I'm gonna have a, what? A decrease of minus 1 times I1, or minus 6 over the square root of 2 at an angle of minus 45 degrees. That means I'm gonna get an open circuit voltage with a magnitude and an angle, right? A non-zero angle. So what does that come out to be? Do it on your calculators. You'd be surprised how many people stumble right here. Until you get used to using it, you're gonna get in trouble right here. This is what? 12 at 0 degrees minus 6 over the square root of 2, whatever that is, at minus 45 degrees. What do you get? Magnitude and angle, please. Anyone? Come on, you guys got calculators. Bring them and use them. You won't believe how much it'll help you.
Dr. Yancey, why is the 45 degrees negative?
All right, downstairs here, it would be square root of 2 at plus 45, right? What happens when you take an angle upstairs? It becomes minus, right? So it's minus 45. All right? You remember doing this kind of thing, right? If you have 1 at an angle of theta downstairs, flip it up, it's 1 at minus theta. That's all it is. So what do you get for this V open circuit? Anyone?
I'm getting 9.49 volts, or yeah, volts at angle of 18.44 degrees.
0.4?
I got that too.
4, did you say?
Yes, sir.
All right. How many got that? Good, good. How many are using 83s here? 83s? 1. 84s? 89s? Anything else? You have something, what is that called, 36 plus or?
This is Inspire.
Inspire? Anybody, how many are using Inspire? Is that the latest and greatest?
Yeah.
All right, well, I'm sure all those will do this seamlessly, but you've got to make sure you know how to do it. So I've got that, and the third thing, right? Now I have to find Z Thevenin. What is Z Thevenin here, class? See, this is a little more complicated, right? What's Z Thevenin? Well, what do I do with these sources to get Z Thevenin, people?
Turn them off.
Yeah, but we better make sure they're turned on. Because I didn't grade that thing, but I have graded these in the past, and you will see Z Thevenin equals 12 volts plus J10 or something. There's no voltage involved with the resistance or impedance. Right? Just make sure you get that. So you turn that off, and now I need that impedance. Well, what is it? How many see this one and that J1 are in parallel? Show of hands. Y'all see that? They are in parallel, right? Right? It's important. This is in parallel with that now, right? So it's going to be 1 plus that. So it's 1 plus, and the parallel combination would be just 1 times J1 over 1 plus J1. Now that's going to have a magnitude and an angle as well, isn't it, class? Give that to me if you don't mind. This one's a little more complicated, and I'm glad it is for reasons, because some people are just used to working with real nice numbers that come out like 2, 4, 0 degrees, 90 degrees. Now this thing's got nothing in it that's easy. So what did you get for the Z Thevenin? Magnitude and angle.
I got 1.58 at angle 18.44 degrees.
Anybody else? How many got that? Okay. I'm going to trust you on that one. All right, if I have that, if you didn't get it, check. Find out where your mistakes are now. Don't wait till the test. Do them now. So that's Z Thevenin. Finally, I build my Thevenin equivalent circuit. And I go ahead and I stick the open circuit voltage here. Then I put my Z Thevenin here, right? Then, that's the terminals where I can put anything I want. Specifically, what I'm going to do is put the load here. And that's minus J1. And I want the voltage right here, V out. So V out right there, y'all agree we have V open circuit, right? Y'all agree we have Z Thevenin, correct? Now to get the output voltage, I do voltage division. So my output voltage here is going to be equal to V open circuit times minus J1 over Z Thevenin minus J1. Now I left it that way. Here is Z Thevenin, here is VOC. You can punch it into your calculators. Get used to doing this. I had electronics right after high school. I didn't go right to college. I got a technical degree. And this one guy was ex-military. He was in 2 tours of duty in Vietnam. And the way he taught us, I mean, we had to spend 4 or 5 hours in classes every day doing this stuff, is get your calculator out and use it. You will not make mistakes if you use it all the time. If you use it once infrequently with imaginary numbers and stuff like this, you're going to be making mistakes all over the place. It helps. Trust me, when I say bring your calculators and use them, it really does help. What do you get for this? I want magnitude and angle now. If you can't get it, I'll try to find somebody that can help you. Anybody? You can see it. It's not instant. You're punching it in and you're learning how to do this on your calculator. But it should be fairly efficient after you get done doing these problems. When you do 20 of these problems, several different ways, on your calculator, you should become extremely good and proficient. Just my thoughts. From my perspective, it's amazing. I got people sleeping, people on their phones, people, I don't know, listening to music. You get the whole 9 yards, everything coming in. All right, what did you get? Anyone? Anyone? Still working on it.
4.74 at an angle of 18.43.
18.43 degrees.
Yes, sir.
Anybody second that? Anybody? No. I don't know. Anybody get something else? Yeah.
I got 6 at an angle of -53.1.
I got that. 6 at an angle of what? Say it again. How many got that? Well, I'm going to tell you, get used to doing your calculators, using them in class, because you're going to see, you'll catch the errors here. I'm not kidding. I don't know how many errors with calculators on the test, but I'm pretty sure on problem 3, in both, for either test, most of the errors were calculator errors. That's, I mean, bizarre calculator errors at that. All right. Now that I've done that, we're going to move into power. I know I only have 10 minutes to do this, but I wanted to make sure that I talked about this in class before we moved on. Now, everybody is an engineer. Here's the term power. In engineering and physics, it has a very unique meaning. It does not mean some per se thing, it's some abstraction. Power is very simple. It's the ability to do work, and it has to do with energy. For electrical circuits, power, the symbol for, this is power. The symbol for power is P of T. And in general, if you have any element here, doesn't matter what it is, and this is going to be a time domain, all right? And you have a voltage across this element, some V of T, and current is entering, I of T, entering the positive terminal of that element. It could be a resistor, could be a resistor capacitor, could be a resistor capacitor inductor. It doesn't matter what's in that box. But if you have the current and the voltage, then the instantaneous power is equal to V of T times I of T. Now V is in volts, I is in amps. Power has the units of watts. The symbol is capital W, and it's watts, named for James Watt. All right, that's power. Now, in mechanical engineering, when you do power, you do horsepower sometimes, right? How many M's in there? Don't you do horsepower? I'm just wondering, it's like I didn't see. You have, there's all sorts of different units for power. Watts is an SI, System International Unit. It's very common to see things rated in watts for any type of electrical circuit, and a lot of times for power drives in motors. However, in this country, horsepower is the most common way of indicating the power, the peak power level in an engine, I think. Unless, I hope I'm not wrong, but that's what it was at least 5 years ago. So that's power, the instantaneous power. Now I'm going to tell you something. What we talk about when we deal with power most of the time is called steady state power, or power at a constant frequency. So what we assume is this. This is generally true. You know when you talk about power and you've got that wall outlet, right? Well, that's a 60 hertz signal. It means it's changing 60 times a second. There's 60 periods really in a second there, 60 hertz is a frequency. It's constant, it never changes, right? What does change is the amplitude of the current coming out of it. Stick a socket in there. Now, when we talk about power and voltage there, the way we render that is we would say V of t here would have some voltage Vm. That's a magnitude. Then it will be given as some cosine of omega t here plus some phase angle, and that would be theta v. Now, this is the voltage. The current, if that is the voltage drives the current. The current will have the same exact frequency. It'll have the same cosine and form. So the I of t here will have I of m, that's a magnitude. It'll have cosine of omega t, same exact omega. And omega, I hope we all know this, is just 2 pi f, where f would be the frequency, the steady state frequency. Yes?
What's the parentheses for the ELEC?
It's omega t plus some angle, it's theta sub v. It's just an arbitrary angle. And it's usually 0. And this is going to be omega t plus some theta I. Now, theta v is just an angle associated with the voltage. It's usually 0, but not always. And theta I is the angle associated with the current. Now, when I look at the power, P of t, right, that's equal to V of m times I of m. Then it's going to be cosine of omega t plus theta v times cosine of omega t plus theta I, right? If y'all remember back in the day when you had to learn all your trig identities, cosine A cosine B is cosine A plus B plus cosine A minus B over 2. Does anybody remember these things? Never heard of them. I don't even know what a cosine is. This is going to be 1/2. I don't care if you know about it or not, you're going to know. And then it's going to be times cosine, and then it's really this angle plus this angle. It's going to be cosine of 2 omega t plus theta v plus theta I. I didn't like them either. Plus, then it's going to be just cosine of theta v minus theta I. Now, please just write that down and go with it. I'm just saying that I use the half angle identity. So it's cosine of the sum of them. It's 2 omega t plus theta v theta I plus cosine of theta v minus theta. So it breaks it out. Yes, sir?
That bigger, please.
Oh, jeez. Not this again. Yeah, I can write it bigger. Under protest. This is not that important, by the way. What I'm going to is important. So there will be cosine of 2 omega t plus theta v plus theta I plus cosine of theta v minus theta I. Just listen to me for a second. I'm going to make life easy for you. Hear me now. This is something that varies as cosine of 2 omega t. You all see that? It varies twice as fast as the voltage or the current. It means power itself will have 2 times the frequency of the voltage. If you look there, that's all voltage is 60 hertz. You see these lights up here? I mean, those lights? Those lights actually blink at a rate of not 60, but 120 hertz. Because the power itself will be varying. It will go from 0 to peak to 0 again every half cycle. Or if they blink at a rate of 120 hertz. Now, most of you know that. Those are just, those lights right there flicker. Does anybody know that besides me? That's 60 hertz feeding that thing, and it flashes on and on. Now, incandescent lights, because they heat up and there's a thermal lag, they give off more or less steady state light, steady the intensity. But those don't. And if you take high-speed camera and take that and slow it way down, you'll see light, darkness, light, darkness. This whole room will look that way. Has anybody ever done that? Have you? Yeah. It's kind of eerie too. All right. Now I have that as the power. Here's what we do next, and I'm going to break it up in a second. What we look for is something called the average power. That is the effective power that you can get out of the wall. Not the peak power, but the average power. So the way we get it is this. You know, most of the time in engineering, you're looking for the effective value of something, not the peak value, not the mid. Yes?
So that P of T, that long equation, is that the instantaneous power?
Yes, it is, and it's because it's a function of time. If you look here, you pick a time, you give me theta v, theta I, and Im and Vm, I can tell you what the power is in watts. It goes to 0 at some point, by the way. Yeah?
What's in the denominator of the last one?
It's not, this is not a fraction. This is plus this. You know, let me just write this down. You know, cosine of A, cosine of B equals 1/2 times cosine A plus B plus cosine A minus B. Anybody remember that from yesteryear? Anybody? Come on, you guys seen it somewhere. You Emmys use this stuff all the time. You can't lie to me, I'll talk to Bush. Oh, got something. All right, now hear me. This is the last thing. All right. What we talk about is the average power. Write it down. Average power. What is the average power? It's the integral from 0 to t, and t is the period. T is really 1 over the frequency right there, and it's also just 2 pi over omega, if you want it that way. There's a lot of different ways to talk about the period with respect to periodic signals. It's going to be, average power is 1 over t, the integral from 0 to t of p of t dt. Now, I'm going to just cut to the chase here because I'm about out of time. I want you to look over here for a second. You see how I have this term cosine of 2 omega t theta v theta I. How many see that? When you integrate a cosine waveform over a period, what value do you get? Think now. Cosine waveform over a period, integrated. What value? 0. Sine waveform over a period, what value?
0.
Cosine waveform, omega t plus any constant integrated over a period is still 0. That means this part right here, integrated, is 0. Now, that is a constant. Cosine of theta v minus theta I, that is a constant value. Are you with me? When you integrate that, well, the average value of a constant is the constant. You follow me on this, class? So this part right there, the second part, means this whole thing boils down to 1/2 magnitude of Vm, magnitude of Im, times the cosine of just theta v minus theta I. Write that down. And that is the average power if you're dealing with a system that has a constant frequency, steady state, and it does not. That's the average power. That's the power we worry about. When you see something like a hairdryer 1,000 watts or something, that's what they're talking about. Now the peak power right here, the power, when you talk about peak power and things like that, I'll get to that, but it's much higher than that. But you don't really care because it's not effectively doing anything other than, a flip. All right, we'll pick it up next time. We'll talk about power on Wednesday.